There are some things about limits that we need to discuss. Sometimes it is most helpful to use your math reasoning and intuition when evaluating a limit. We're not always going to have a graph or going to have a table of values to determine whether the limit exists, whether the left-hand limit exists and the right-hand limit exists, and therefore the overall limit exists. You know a lot of mathematics by now, so make sure that you have your math reasoning brain on when you're dealing with these limits analytically. Additionally, technology is not always completely accurate when we're exploring what's happening near an input value that doesn't normally give us an output value. When we're exploring discontinuities, your technology can fail you. So be very careful trusting your calculator solely without verifying your results. And this is where I would say look closely at a table of values. Your table is going to tell you much more than your graph on your calculator will. Does every function have a limit everywhere? We just saw examples of functions that had limits that existed at the input values where we were exploring. Is that always going to be the case? Is every function that you've ever dealt with, is it like the functions in the examples? If not, then we might have functions where the limit doesn't exist. And what might that look like? Here is an example of a piecewise defined function where the function has two completely different behaviors over different pieces of the domain. For all input values less than 2, the function acts like this line, negative 2x plus 5. For all values greater than 2, including 2, it acts like this line, x plus 1. And we have them graphed, and we have our table of values. This function is well defined at x equal 2. There is the point x equal 2. When I put 2 into this function, I get a well-defined 3 out. You can see this function is well-defined everywhere. We don't have any problems with not having an output value for every input value. What we do have is we have this jump here in the graph. And so when we talk about what's happening to the output values as we approach input values of 2 from the left and the right, we're going to use the limit. So the limit as x approaches 2 from the left of our function is this part of the graph right here. As we approach input values of 2 from the left, we approach on our function output values of 1 from above. Again, we can see this on the table of values as well. As we get near input values of 2, but smaller than 2, we get near output values of 1. Let's see what the right-handed limit is doing. The right-handed limit, the limit as we approach 2 from the right of our function, is right here. There's inputs as we approach 2 from the right. Here's the graph of the function. And as we approach inputs from the right, the outputs from above approach 3. So the limit as x approaches 2 from the right is 3. Well, the overall limit as x approaches 2 of this function can only exist if the one-sided limits are equal. The one-sided limits are not equal, so the overall function does not exist. We don't say undefined in the limit, we say the limit does not exist. That can be written in a shorthand of capital D, capital N, capital E. Be very careful with writing the equal sign when you determine a limit doesn't exist, because the language of that would be the limit as x approaches 2 of my function is, that means equals, if you write the equal sign, is does not exist. We don't need the is, so make sure if you have a does not exist that you do what I did, because it's our habit to write equals. Well, you can write an arrow on the right side of the equal sign, and that just means implies or gives. And then you can write does not exist. So there we are. There's your introduction to limits. There's your introduction to calculus. So the idea of the limit may seem simple, but what previous mathematicians in history did with that idea is phenomenal, and that's what we're going to explore this year.